Hello. In this video we will introduce the concept of potential energy, and we will explore the potential energy of gravity. We have already seen kinetic energy. It is the energy associated with an object's speed and mass. However, an object can also have an energy associated with its position, and we call that energy a potential energy. Why should an object's position be associated with its energy? Well, this happens when certain types of forces are acting on an object and doing work. The best way to explain this is by thinking about gravity. Imagine you have an object on the ground, and you lift it up 4 meters. Let's think about the amount of work you had to put into the object to get it that high up. The whole way up, the box was feeling a downward force of mass times g, and you lifted it along the same path as gravity, 4 meters. So we take negative mg, which is about negative 10 newtons, and multiply that by 4 meters to get negative 40 joules. That is how much work you did to lift the box. But now the box still isn't moving, so you haven't increased the kinetic energy at all. So where did your work energy go? Now it could be that it was just lost to some other object, like what happens when you push a box against friction. But we'll see that that's not the case here. After all, if you drop the box, then gravity acts on the box and it will fall the same distance. So gravity now does work on the box like this: negative m times g times negative distance. This amounts to 40 joules of work. This time, we know where that work energy goes. It goes into the kinetic energy of the box, since it will have picked up some speed before it hits the ground. Where did the energy to speed up the box come from? Well, this is how it works. When you lifted the box up 4 meters, you did 40 joules of work on the box. While the box didn't gain any kinetic energy, it did gain potential energy, which is the energy associated with its higher position. More specifically, it went into the box's gravitational potential energy. We call this energy potential energy because it always has the potential to turn back into kinetic energy, which is just what happens when you let go of the box and let it fall. So potential energy is a number associated with an object's position. In the case of gravity, we write this equation here. U equals m times g times h, where h is the height, u represents the potential energy. So for gravity, the only part of the position that matters is the height. Where you measure the height from is your choice, so long as you are consistent. There is a handy formula which tells us how much work is done when the potential changes. W equals negative delta U, or the change in potential energy. Perhaps in a more helpful form we would have this. This basically means that work is dependent not on the value of potential energy, but on how much the potential energy changes. It also says that if the potential energy increased, then the work was negative. This is because energy is transferred from the object's kinetic energy into the potential energy, and we treat the reduction of kinetic energy as negative. If the potential energy decreased, the work is positive, which means that the kinetic energy increased. So as a quick example, if a ball falls from a height of 10 meters to the height of 8 meters, we can calculate the work done with this formula. Plugging values in, we get this equation, which results in positive 20 joules. Again, this means that 20 joules of energy was transferred from the potential to the kinetic energy. Now, we mentioned before that potential energy can be easily converted into kinetic energy, and kinetic energy can be converted back to potential. We can understand these energy transfers with these two equations: the equation of work from a change in potential that we just saw, and the equation of work from a change in kinetic energy, which we saw in last video. When talking about an energy transfer from kinetic to potential, or vice versa, the energy is transferred via the work in these equations. The energy transferred from the potential equals the energy received by the kinetic, so we can set these two equations equal to each other. So let's look at an example of this. We have a car at the top of the big drop in position A. At this position it has kinetic energy of 1000 joules. What will be its kinetic energy when it gets to position B? You ought to be able to solve this if you pause here and work at it. Okay, so we really just need to use this equation, where we set the negative change in potential equal to the change in kinetic. We just need to solve for the kinetic at the final position, which is position B, which just requires us to move the kinetic at the initial position to the other side. Now, the potential in our system is mg times height, so we can write this equation like this. Great, now we just plug numbers in, and we do the arithmetic, and that's it. The final kinetic energy is 21,000 joules, or 21 kilojoules. So let's summarize what we have learned. Potential energy is an energy associated with an object's position. The gravitational potential energy is given by this formula, so it is dependent on the object's height. We have also learned that the work done by a potential force is given by this formula. Finally, we saw that to see how potential and kinetic energies are interchanged, we can use this formula, which just says that the work done by gravity goes into the object's kinetic energy. And that's it for this video. Thanks for watching.